All right, let's begin. Right. So today we'll be continuing and wrapping up on memory. The last technical concept that we need to cover before we finish is virtual memory. So we are finishing up the memory in terms of addresses, how they are being used. Then we'll end with virtual memory. The rest of the class is the research paper and any other IT issues we have to learn. Right. So memory last time, what we said was that memory, there was virtual address and physical address. Right? And you realize that if you have memory, some of it may not actually be memory that is really there. So for example, you can have a seat number, but when you get there, or a ticket number, when you get there, then you actually get assigned to a real physical seat. So the same idea we have for human beings. Like you're going to buy a plot of land, for example, they may give you a lot number. But when you get there, then they'll tell you that, oh, currently this is the lot and the specific GPS corresponding to that. So the same idea is used in OS. There's virtual address which is given to the processes. And when they're actually running and need a space, that address can be given what? A physical address. Right. Now the three addresses that we said were important was the base, that was the lower limit. The limit is the maximum you can use, and then sometimes, because you may move around, you have a relocation. So if you have an address, we add relocation. We also said that to create an address, it can be created at compile time, meaning while the program is being turned from human language, like C++, into assembly. It can be created at load time. Load time is when the program is being set up to run. That is when it can determine the addresses. And that's usually good for, the addresses I said that were good for that, we discussed two. The first one was the static addresses, or absolute. Right. That means it's tied to a specific physical address. If you compute that, it doesn't mean that all compile time addressing has to be static. At compile time, it just means that it's going through a programming language to decide how to do the addressing. But at that point, if there's anything that has to be absolute fixed, you can decide that this program has to be in this portion of memory. Right. At load time, that is when you have clicked the program and it's being brought into memory. The OS can put things together. And at load time, we said there were different types of libraries. So for libraries can be static, right, or dynamically linked. Right. So if you have a library that uses certain function calls like fopen and so on, statically linked means that the OS will look at the code that it has. So every OS, so if you take Windows, for example, if I picked, let me see, if you go into Windows, see if I can find some DLLs, right? Just search star.dll, right? So DLLs are all these dynamically linked libraries. So Windows can have many of these, meaning that some programs, let me see, can have these. So there's system.data.dll. So all of these means that there are some files that are not necessarily programs, but are what? Groups of libraries. The same way that in Java, you can compile, you can have a Java file that has many libraries in it. Right. So the question is, at the beginning, if you say statically linked, that means that he knows that there's a specific file and there's an address location where he can find that function. So that means that that address can be loaded statically. That means it's always there. Dynamic means that when it's going to run, then it can go and find the file and the library function to use. Right. So those are the two things when it's being loaded. Execution, the libraries that are dynamic could also happen at execution time. Execution time is while it's running, some addresses are not known. But then if it makes a function call, it could then go and say, let me go and find it. Or if you want a variable, and then say, let me go and find it. So at execution time, addresses may be found as well. And we ended off by saying there was first fit, best fit, and worst fit. First fit was, if you read the text, it's the easiest one. It means the first space you find, use it. Best fit is try and find the space that is closest in size. It's almost like you're going to sit in a car, and instead of giving you one long seat, they'll look at your body structure and give you a chair that is closest in size to your body structure. So I think I see some shortcuts that do best fit to make sure that. Okay, so worst fit just means in order to not have. So if you have, let's say, a slim person sit on a medium seat or a medium person sit on a big seat, there are going to be all these spaces left over. So the idea is for worst fit is give the longest bench you can have. So if you maybe put a slim person on a very big seat, Hopefully you can fit 2 slim people in a big seat. But if you have been fitting the medium to the large, the small to the medium, then you have all these spaces left over and nobody can get anywhere to sit. Like someone will be sitting, half their butt cheek is on one seat, half their butt cheek is on another seat. But then if you have 2 slim people on a big seat, that's nice. Usually in the front seat of Protros, we see that happen. Right? So that is the idea for worst fit. So today we discuss ending of address management. We'll talk about virtual memory on Monday, but today we're going to end up with all the things about how addresses are computed. Right? So before discussing how addresses are computed, one idea to discuss is fragmentation. Right? So anytime you allocate space, fragmentation, so if you look around class, there are all these spaces. Anytime there's space that's unused, it tends to be, so fragmentation just means you have broken something and there are pieces left over, like there are fragments, so pieces. Right? So if there's fragmentation, there are 2 types of fragmentation. So, right. This confuses people, but please, when I say you don't understand, just ask and I'll give you more examples. When we say fragmentation, there can be internal fragmentation. So for example, in this class, internal fragmentation means that within the class there are spaces, so there are chairs available. Right? And external fragmentation is fragmentation that is outside the allocation. So if there was another sitting area, maybe a classroom, that is outside the use of any course. That is considered to be external. So anytime there's an allocation of memory, the allocation can be given to a process. If the process is using it and doesn't use all the memory given to him, that is the internal. It's just like if Ghana were not using some parts of the country, that would be considered to be internal fragmentation. That means there's a piece of land within ourselves that we are not using. That's internal. External means that even though we have allocated, so imagine if there were some empty spaces in Africa, currently no empty spaces, but there were some empty spaces between countries and nobody has laid claim to it. That's considered to be external. So that means for the processes, there's some space that is external, that nobody is using and it's left over. Right? So there's internal and external. So people are always asking, oh, which method should I use? And the thing is really, as far as fragmentation, can I please? So external fragmentation means that space that is outside the allocation. For example, if I'm giving out blank sheets for a quiz, right? And I give everyone a sheet. Oh, I used to have, hey, someone is taking my stack. Is this a plan to slow me down? Okay. I'll bring my stack. Right. So if I give out the white sheets and everyone writes on it, the space that is left over on your own sheet is your internal fragmentation. So internal means that for a process that owns space, the unused space within him that you can't use, you can't give it to someone else. So someone can take one sheet and write on a half. The other half you have not written on is what? Internal. It's internal fragmentation. So processes that take memory, that's the issue of internal fragmentation. External fragmentation will be the sheets that hasn't been given to anybody at all. It's there. But maybe the exam requires, let's say, 4 sheets. And if I have 3 sheets, that means that maybe nobody can write another exam because I don't have enough sheets for a person to finish the exam. So external means that there are some allocations that I have not given out yet. Okay, so the external ones, the ones that are external still belong to the OS. He has not given them out. Yeah, so the blank sheets. So for example, even though you are seated on these tables, right? There are some parts where people are, so if you take the table space itself, on some places she's sitting here. So if I give her some space, this is her own space. This part for her is an internal fragmentation. She's not using it. Since she's not sitting here and nobody is using this part is external. So she owns her own space. But even though she owns her space, she's not using all of her space. That will cause internal fragmentation. Right. And the external fragmentation is the space that hasn't been allocated at all. And it's there. Right. And that means that no process owns it. But the problem is, so there are 2 problems. If there's internal fragmentation, it means that people are wasting space. Even though you have given them, so it could be land, it could be books, that means that they are using some and are not using others. That means internal. External means you have not given to anybody at all. So you can have, let's say, an area where people have built land. I think you may see this in some villages. Okay, not villages. If I say that, people think it's just villages. You can see it also in the town. that there are some areas where the space is too small for a house and it's too small for a street. We can't really decide what is useful. That means that in the planning of the area, there is external fragmentation. Internal fragmentation would be that someone has a piece of land, he's not using parts, he's just sitting on parts. That means that there is internal fragmentation, an unused space within. Right. So if you are giving out memory, you then have two concepts. Either you give everyone the exact memory or you give him more than what he needs. And some people say, why should you give more? If you don't give enough, so some of you have written these Java programs, and as the program is running, someone clicks, says, make new student, make new lecturer. If you don't give enough memory, every single few minutes or every sec, you'll be asking for more memory. It's almost like when I don't give out enough paper for you to write your quiz on. If I give you too much, I've wasted the paper. If I give you too little, like if I give you just one sheet, then and you are going to use 8 sheets, I'll be going around the whole time, just chasing people. So they came up with the idea of the examination booklets, which has many, many sheets. In the examination booklet, maybe there too, you can see internal fragmentation. Internal fragmentation means that what? Someone has written on some and has left, and it's wasted. Nobody can do anything. But at the same time, if they didn't give you enough, you would spend a lot of time running around trying to give out sheets. So there's this trade-off between, you can give more memory than the person needs. You can try and guess and give some estimate. Or you can be statistical. You can say, oh, anytime that Microsoft Word runs, it tends to use maybe 4 megabytes. Give it 4 megabytes for it. As the next time when it's running, you can give it about 4 megabytes. If it asks for too much, you can keep some statistics to say, oh, this program tends to use on average this amount. Right? So you can allocate more than the person needs. You can also decide to allocate the exact amount, and that would be very nice. That means no internal fragmentation. But the problem is, if the person keeps asking you, you have to keep responding to give him the exact amount. Right? So those are the two issues that are there as far as allocation. So any questions about internal, external, and whether or not you over-allocate or allocate exactly?
So when we say that this defragments into does it defragment internal fragmentation or external fragmentation?
Okay, so that's a good one. So if you pick your hard disk, so I'll do a very small example just to illustrate that one. So if you pick your hard disk also has a way of breaking up pages. I'm going to make a very small file. I'm just going to call it, and I want to make a folder. Oh, he's not going to let me make a file here. Okay. Maybe this is a shared drive. You let me do this. Okay, so I'm going to make a file called my.txt. It says 0 kilobytes. If I right click and say properties, right, it's kind of small. There is size and size of disk. Sorry. I'm just going to make a snapshot and zoom in. Click. Right. So this is a file I just made, and it says size and size on disk. It's 0 bytes. There's nothing in there. Right. I'm going to take the same file and just put in 1 character, and then we'll look at the same size and size on disk. Just to show a point. Okay. So I open it in Notepad. It's blank. I put in just 1 character, A. I save it. Right. And if I go to properties, right. Sorry. Right. Size and size of disk. It's using 1 byte. It will take a while for it to update size on disk. Let me add a few more characters. So what we are going to be seeing is when we add more data into it, more, save. Okay. Oh, okay, so I think my Windows is misbehaving. On the side, you can see that he's saying he's using 1 kilobyte. Sorry, let me just. Copy to clipboard. the user interface, sorry, the new Windows, I realized it's not like an error. It's just, it takes a while for it to update some of the information. Right. So the size for the file is now saying 1 kilobyte. Right. But you realize that 1 kilobyte is 1024 bytes. But if you look at the file I made, there's no way I've typed 1,000 things in there. Sorry. This is a small file, right? This is obviously not 1,000 items, but it's saying it's using 1 kilobyte. So it means that for the 1 kilobyte that's been given to this file, some of it is what? There's internal fragmentation there because he's using parts. The rest of it is what? Is wasted. The external fragmentation means if you take the hard disk itself, so the same concepts you are using in memory, the same will go into the hard disk as well. If you take the hard disk, there will be some spaces that are used and some spaces that are not used, right? So if the OS is also arranging files and it doesn't place them properly, it's possible to have little spaces that are left over. Currently, Windows has this tool. It used to be very graphical, but the defrag. But these days, I've seen it doesn't have. Yeah, it just does. Sorry, there was one that does it. Okay, defrag. It used to have a very nice. Oh, I clicked something else. Defrag and optimize drives. Come on, I clicked you. Right. These days, it doesn't say exactly what he's doing. Like, you just click and say optimize, and magically it tells you that he has optimized. This is a solid state drive. In a solid state drive, it doesn't do rearrangement. Right. In solid state, the idea for solid state drive is it takes the same amount of speed to get to all the address spaces. So in solid state drive, what he instead does is to trim, which is to try and see which blocks he has been using a lot and which ones he should not move around, but sort of keep track of which ones he should be using. So trim if he's left some. So in a hard drive, there could be some space that he says, oh, I'm not using it here, but he's not gone to actually mark it that it's not used. Because when he's searching for something, he has a list he uses. So he can go through and so for speed. So remember we said things like first fit. For speed, the OS does a lot of things. So, for example, even though I was right-clicking to say what's the size, it was saying 0. But if he goes in and does the actual statistics, he can check and say, oh, it's not actually 0, it's 1 kilobyte. So in the OS itself, there seems to be some delay between what parts of it are saying is 1 kilobyte. And let me see if it's updated now. It's still saying 0 kilobytes. This is a serious problem. Okay, not that serious, but it's not good. Right. So the solid state drive people tend to use trimming. When you say optimize, he would trim. But for those that are using the hard disk that have the spinning thing, when you say to optimize, you see he would arrange the blocks and then start shifting them, trying to arrange them so that a file will organize will be continuous. So when he's reading, he can read all together. Right. So I think they have changed how things behave. Never been run. Needs optimization. Okay, let me stop before I freeze things. All right, so back to this. So we have internal fragmentation. That means the one that's been allocated to processes. Some data within the process memory is not used. External means that nobody has it and it's not being used. Right. So let's look at different ways that addresses can be calculated. Right. So the first approach to addressing. So last time I hinted at this when I said that in a hotel. So. Right. Oh, come on. In a hotel having multiple locations, right? Different processes, for example, the campus could have different addresses for different rooms, right? So there are different people coming from the same organization, but different people will be going to different rooms. If we use that concept, we can say, okay, if we have a program, the program has several different parts, and I know people have not seen or thought about all the parts, but sorry. So there are some which are for functions, the stack. Symbol table is if you have a program that's running, like if you have PHP that's running, he needs to keep track of every variable you declare and where you find it. So if you've not heard the term symbol table, that's what they mean. So a symbol table is just a table containing all the names of the variables and the locations. So it means that if I had a program that was static, I may not need a symbol table. I could just sort of put the exact address for where the data is. But for the programs that tend to be dynamically allocating variables and so on, sometimes it may need, or not sometimes, it actually needs a table containing every variable you have declared and where it will find it. Right? So that if you declare int I, it will say, okay, I have I, currently it is in location 1. I have j, currently it's in location 2. So that's the symbol table. Right? So a program can be broken into different parts, and that means that in the first class, when we talked about base and limit, for each of the parts of the program, there can be a base and limit. Right? So for the stack, there will be a base and limit for that one. So the stack is in one place. For the heap, there's a base and limit for that one. For, let's say, if you have some functions that you have declared, there will be base and limit for those. Right? So if it's able to do this well, then now that means that when it's doing memory, the address is going to be broken into two parts. The first part will be a segment that has a limit and a base. Right? So a segment would then be, so it would be, if I take an address and I break it into two parts, I'll do a small example after this. I take an address, I break it into two parts. One part is a segment, that means some address, part of it telling me that, oh, this part belongs to this program. But for that part, there's a base and limit. And then I have a range. So for example, if I wrote, let me use any number. Where's my Excel? Right. Zoom. Oh, sorry. Right. So if I had a program like Notepad will have different parts. There is the binary code. There are maybe some variables and some functions, right? So it means that if I write an address, so an address is just a number indicating where it will be in memory. So if I write something like, this would be, let me do this. Okay, so there's base and limit. So what you'll be doing, so what the OS will do is, anytime a program is running, right, he would sit there and say, okay, for this program that is running, the binary code, where is it located? The lowest address will be the base, let's say it's starting from 1000, and the limit is 2000, right? Now I would say, okay, I have some variables. So say, okay, I'll put you in address 4000. The limit would be, let's say, 3000. Functions, maybe put you in 5000. Your limit, right, is 10,000. Right. So if you look at this limit very carefully, there is a range that is for that limit. There's like within the limit, I can write them from 0. So if you take this one, the range here. This one is, 0 to 2000. This is 0 to 3000. This is 0 to. So remember that usually they add the limit to the base to decide what the final maximum is. The limit was like, what is the maximum that you can stretch from the base, right? So that means that if I give any address, for example, if someone says, go to address 1020, some of it is for the segment, and some of it is for the offset, right? So this means that, right? So any address that you write for the segment, for this approach, some of it is for what? The segment, and some of it is for the offset. So it means every address, you can break it into those two parts. There's a segment of memory where it's supposed to go to, and then an offset for it. So one thing I can do is, it's not a trick, but I can tell the program, okay, I'll map these. So you are in segment 0, as 0, segment 1, segment 2. So that means that as far as the process is concerned, he can say, oh, something like, where did the things go? So instead of using this number with the actual base and that offset, instead he can say, instead of this, he can say, sorry, let me put these together so you can see. Oh, come on. This is a little bit more data structures than just OS. That's why OS, there were so many requirements. If you know some data structures, if you know some programming, you should be fine, right? So in programming, so that means that instead of using this whole long thing, someone can say, sorry, let me do this, equal 0, 0. Oh, why doesn't he like me? Right. That means that when I am using this segment approach, okay, so let's do step by step. I have a program, Notepad. I want to manage it. So for Notepad, it has different segments that it will use. It has part that it wants to use for binary code. It has a part that it wants to use for variables. So variable, for example, the things that you're typing, Notepad will have to store it somewhere, right? And it has some functions. So the functions are the things like, if you click the file menu, it has to do something to get what you want. If you're highlighting, so there's some functions that it's going to be running. So we have broken it into all these pieces. And so what we are saying is, we can number the segments, 0, 1, 2. So if you had, let's say, Word was also running, he will also have some binary code. He will have some variable. Okay, let me just use binary code and let's give him stack. His segment, I'll keep numbering the segments. So what an OS will do is, when you ask for memory, so because I've given away 1,000 and then offset of, oh wait, this will not work. Realize that the offset is eating into the other one, right? So please note, so here, if the base is 1,000 and the limit, that's what is going to be added to it, is 2,000. That means that I'm using 1,000 to what? 3,000 for the first slot. And I have 4,000. Let me use limits. So 0 to, sorry, let me do this. The absolute address that I can use, so let me write, and this he has 5,000, and I'm going all the way to 15,000. Oh yes, sorry, all right. So I have these ranges that I can use. So at first, we're saying that every process you just be given one block, but realize that that may not be for the best, right? If you make it this way, then you can have something which is more dynamic, so that people can stretch different parts of the program depending on his need, right? So usually the heap will get some space, the stack will get some space. It doesn't all have to be what? One long continuous block. We can break it into segments. But if we break it into segments, then what the OS will do is he will number the segments to manage. So he will say, okay, you have segment 0, you have segment 1, segment 2. So for everybody, you say, okay, your binary code is in segment 0. Your variables are in segment 1. Your functions are in segment 2. Next person, your binary code is segment 3. Your stack is segment 4. But for each one, what you do is, so let me keep allocating. 3,000, limit of 1,000. Meaning that he's going from 3,000 to 4,000. And then let me get some extra space. I would say 5,000. I have to be careful I don't. So when you allocate, you have to make sure that you don't overlap. Right. But would overlapping ever be necessary in this approach? Would I ever think of overlapping, and why? So what I'm doing is, anytime you're asking for something, I'll give you a segment number, and every segment number has a base and a limit. And I'm asking, would overlapping ever be necessary in something like this? Would I ever need to think of shared memory? What does it mean for shared memory to happen? If I'm saying I'm sharing memory between two processes, it means that what? Some parts of them are overlapping. So with this concept, we are now leading into that idea. So it's not just going to be, oh, you have one block of space all for you. I can have different segments and say, okay, 2 or 3 people should share the same program code, which is logical. Because if I have Notepad running multiple versions, it will be good to what? All of you share the same program code. But maybe you have different variable segments. And so, let me move this guy to a higher number, 20,000, 1,000. So let's go from 20,000 to 21,000, right? So it means that now, whenever you ask for something, your address can be composed of your segment number and some offset, right? So this is what I mean by a virtual address. So your virtual address, so previously we were just doing virtual addresses that were just what? I give you an address and I try and find a mapping. But we're not discussing how exactly the mapping was happening. So this is one approach. I can give you an address so that when you say, oh, I have an address that is 0. So part of the address will be the segment number and part of it will be the offset, maybe 30. This will mean that it means go to segment 0 and within segment 0 there's some offset. So if I go to that segment, I know what? I know the base. So if I give you maybe 0030, I say, okay, 00, that is, so this address, this means segment number, comma, offset. So that means your address has two parts, a segment number and an offset. So if you give me any address, I'll go to your segment, figure out what the base for that segment, add the offset to decide exactly where I'm going. I hope people understand. Or if I give you another address, like if I say an address is 0250, that means that there's part where I know, okay, this part is the segment and this part is the offset. So knowing the base and limit, I can figure out whether or not the access should be allowed. If someone gives a number like, let me do this, 0214, okay, let me 01, right. Something like this, you can see that part of it, sorry, this, my format has been taken over. What was it, 021, okay, I think I was trying to do this, okay, cool. Yeah, he's left it alone. So that means that part of it is my segment, but when I get to the segment, I will use the base, and then I'll look at, oh, what is my offset? Is my offset going beyond the limit for that segment? If the offset has gone beyond the limit, it means that what? I am now outside of my memory. I am now going to be what? I have to be stopped for some reason because the OS is now managing. So you can think of this as, it's almost like land allocation. And then when you come, you have a range to use. So you say, oh, land number 0, up to 1 meter. Land number 2, up to 3 meters. So now, the idea for addressing, we can use this sort of virtual addressing approach where you get a segment number. And every segment number, the OS will map and figure out there's a base. And for the base, he knows your limit. So if you start building and then you go beyond the limit of what we've given you, that means that what? You are causing an error of one kind or another. Like you are violating your memory space. I hope people understand. I hope that this is just like, it's something like people can, I don't know, is it internalized in some way of their lives. OS, at some point in OS, it becomes more about algorithms, these ideas, these techniques. That is all OS is. Algorithms and techniques. Don't think of it as, oh, this is computer science, I'm strange, funky. It's not strange, magical, anything. You will see this in filing systems and so on, or even in a dictionary. There's a page, go to, maybe someone say, booklet number 1, page 6. Booklet number 10, page 4. If you go to booklet number 10, and there are only 3 pages, for someone to say booklet number 1, page 3 is like I don't know, there was this thing where someone would sometimes quote a Quran verse or a memory verse. You mention maybe 6 John chapter 4 verse 2. And you ask yourself, is there something like 6 John? How many books of John are there? So it's the same idea. Everybody should have what? A segment. And the segment has what? Some offset that he's giving you. So given an address, you can figure out whether or not you are allowed to even use that address. That is the same idea. You use it every day in everyday life. Like if I said, oh, Ashesi, go to room number 314, you know I'm lying. Right? Is there a room 314? Maybe. Okay, let me pick a higher number, room number 901. You know that it's not. If I say go to Ashesi, room number 901, there's no such room. All right, so let me use the buildings as an example, right? So if I went to, I think Legon is much bigger than us, right? So if I said, okay, go to the academic departments of Legon, go to the 6th department, that will make sense. That when you get there, they have more departments than we do. So if someone says the 6, you go and say, okay, where are all the departments? 1, 2, 3, 4, 5, 6. Right? So that means that anytime I say Legon, you have an idea of a location where you have to go, the base. And then there's an absolute offset. But if I say to go to Ashesi, department number 6, you know that already our limit is someone can add engineering. It's okay, engineering, electrical. But in reality, there are only 3 right now. There's engineering, CS, and BA. MIS people are between BA and CS, right? So if I say go to Ashesi, department number 6, you know that the base for Ashesi, maybe this is our location. But our offset is what? What's our limit? Our limit is 3. So for someone to say go to Ashesi department number 6, it doesn't make sense. Because the department numbers that you are asking to go to is beyond. I hope you understand.
You just said the option and said limit.
Okay, so a limit is the maximum offset you can have. So if I take this room, how many chairs are here? 79. Okay, someone is saying 79. So if I say go to room 216 and sit at chair number 82, that means that what? I am beyond the limit of what I have. So when I'm giving you a location to go to, there is some location, which is like your segment number. And then within that segment, there are all these addresses that are there. But there's a limit to it. So if I give you an address, and I say, okay, but it could be possible that if I say, oh, go to, I think we have an auditorium. Well, I don't know if we are calling it auditorium. I have to learn all the names. Say, go to the auditorium. I think it's just the engineering. There's this big room. The name. Please, gently, slowly. The name. I don't know. It's not a multipurpose room. There's a room here. Oh, so it's now called multipurpose hall, which is different from a multipurpose room. Okay, so if I say go to the MPH and sit on chair number 82, there in that context, it makes sense. Because for that base and the limit of how many chairs are going to be in there, that makes sense. But for this room, it doesn't make sense. So the segment approach means that for any address, you have a segment number and then what? An offset. But for every segment number, the OS has to keep track. It's just like the rooms. When you are doing registration, course registration, there's a base and there's a limit. So if we are giving ID numbers, we know that this is where for the class. So usually we number, that's how the acronym sort of works. We number, we know how many we are to allocate within a class. So the seats are there, so Eleanor enters some seat number. So that's a limit. And as students are registering, if you leave your seat, there's some rearrangement going on, but we know that this is seat number 1, seat number 2, seat number 3. Same for exams. When you come to exam room, on exam day, she has this sheet where she has an idea that since this number of people have paid, and if you haven't paid, please, you have to make arrangements for something, I think. So don't say, oh, I haven't paid, I'm running away to go home. If you haven't paid, just speak to the accountant, they make arrangements. And then you'll say, okay, these are the number of people who want to come. So when she enters the room, she's just going to look and say, oh, as far as I'm concerned, this number of people should be here, 50 or 60. And then, if she realizes that someone comes and says, oh, I'm on seat number 61, she'll just say, but as far as this class is concerned, we have only maybe 60 people. And you're saying seat number 61. But for another class, maybe programming 1, where there are 150, same seat 61 programming 1 makes sense, given the base and offset, that segment of programming 1.
If the offset exceeds the limit, it just means allocate. So what happens?
If you are exceeding the limit of what is allowed for that segment, then that means that the program has to be stopped. So the OS will normally kill you. Right? That means you are trying to. So that's why for most programs, the safest way. So Java has been providing a nice way. In Java, you just say new. You don't deal with the addresses in Java. I think those who are now taking programming 3 will tell you that in C, C++, you can make up your own addresses. But of course, if you go beyond your scope, you will be killed. But Java is much more safe. In Java, anytime you say new, you ask permission very nicely. The programmers don't have to worry about, okay, if I'm in an array, if this is a string, if I add +1, I am at the string's first position. In Java, you don't worry about those things. In Java, a lot of things are, array index. If it's a string, there's an array index. You don't worry about the specific calculation. In C, for those people, you can worry about it. It can be more efficient.
Yes, example. So the segment number is 2, and the offset is 1.
Okay, so that means that I have I won't go over. For this one, I won't go over. But if I did, okay, let me add another one. 0, 1, and I do the same thing, 1, 3, 3, 3. In this case, I am going to what? Go over for that one. So for every address, now you're breaking it into a segment and some offset, so that you can say, okay, this offset has this base, and there's a limit for that. Right. So back to this. Sorry. So that means that every segment, that's all that this diagram means. The book has nice diagrams, but some explanation involved. So all that this diagram means is that anytime you are given an address, the CPU is given an address, he's going to take the segment number. We use that segment number to go and find the limits and the base. We'll find those two numbers, right? And then he's going to also look at the difference to see, oh, if I use that one and I add it into what you have there, your limit and your base, will I be going over that one? Will I go over your limit? If I don't go over your limit, fine, you can go ahead and access memory. If I'm going out, then it means that what? I have to be stopped. Right? So this is just a simple diagram that is being used. I just put on the side the idea that you can now be having in a program different, scroll down a bit, different areas of the program. So the program can now have different areas. That means different segment numbers. And for every segment number, I can have one base. I've just used base 1, limit 1, base 2. That means different numbers to represent them. In order to do shared memory, or for programs to have the same parts. So for example, if I have a program that's running Notepad, I'm running 3, 4 versions of Notepad. I don't have to make multiple versions of the same binary. I can just map your binary the same. I'll give you the same base and limit for all the people who are using Notepad for the code part. So that whenever they are reading from that part, they are reading from what? The same part of memory. Are people understanding that part? That idea that you can use this to accomplish some amount of sharing, right? In that, if where the Notepad were to share space, I just have to make sure that I map the segments to the same segment number, so that the same base and limit, so that you can accomplish this sort of sharing. So when I'm going to get something for you, I go and look to see what's your base. Oh, it's the same base. What's your limit? The same limit, and you can share that way. Okay, so the next thing, so this was the next page, saying the trick we can play is we can map two processes to the same space. We could share by just mapping. That was what I was saying. Right. So the next concept is paging. So they are just two different variations, right, of the same idea. For the first one, why I said we are just going to use base and limit. That one, the limit can be variable. It's just an integer. So that means that I can have all the sharing. But then, even if I don't have... so remember we said there can be internal and external fragmentation. When I'm allowed to give you an arbitrary limit, I can often try and solve this internal fragmentation. Remember, there's internal means that you are using space. And then there's some space in you that you are not using. If I'm allowed to, so for example, if I'm allowed to, instead of have pages that are like this, these are, currently these are what our printer pages look like, A4. There's a defined height and width. But there was a time, I don't know if people have seen those printers, where the paper in the printer is a roll. It's a roll, and as you are printing, so if you print like half a page, you can take the half page and tear it out. The receipt booklets are like that, the ones they print the receipt on. The printer page is a roll. Right? If it is a roll, it means that they can arbitrarily set the limit. They are segments. He's setting the limit himself. If you can set the limit yourself, then you don't have to, or you can solve the internal fragmentation issue, right? Is everyone cool? If you can set the limits, then you can solve that issue, right? But then, if you can set the limits, and the problem with an operating system is that people are coming and people are leaving. And so it means that over time, you give the space. Maybe at first it was consecutive, but when someone leaves, there's a block, there's some space there. And the space is now arbitrary. Maybe you give 13 to someone, 13 has come back, there's now a 13 space there. Right? And the next time you are allocating, you will not be able to, you can't guarantee that the next person will be using 13. So if someone uses 20 amount of space, comes in, he leaves, he has left 20 for you to allocate. So it sounds nice. For the one that you are printing the receipt, it's just one time. You print, you don't waste any space. But you can consider that if we're using fixed sheets like this, like an A4, to do all the printing of receipts, sometimes you use part of it, sometimes you don't use the other part. Right? So the same way that currently now we use pages, in the OS, they came up with the idea that, okay, why don't we take the memory and break it down into blocks? Because whatever happens, it's almost like people are going to come in and go out. And so if I'm arbitrarily giving space, like, okay, I'll take 21 to the first person, 31 to the next, 74 to the next, 100 to the... Now, when these people come in and they leave, then there are all these variable spaces that have been left for me. So instead of having to deal with that, so if you are allocating that one in this... if you are using the segmented approach, you decide your base, you decide your limit. You can prevent internal fragmentation. But then external fragmentation will become an issue because the spaces that people are using and leaving, right, they are not going to be fixed size. And you can't guarantee that the next person coming in will use the same space. So Notepad runs, he uses a certain size. If Word is the next to run, there's a space there. Word may use or may use less. So whatever you do, external fragmentation may start to creep in. So the idea is, why don't we break the memory into pages, fixed sizes, right? And so, there are two concepts. For a program that is running, let me see if I can get one of my programs to show the task manager. Task manager, show. It's taking a while. I don't know why he's doing that to me. Oh. Okay, why? Process. Okay, my task manager. Okay, good. Showing. Okay, so don't change too much. All right. So one of the things that you would see here is that every program that's private bytes, right? Every program has some amount of information that he's working with. So as they come and they leave the memory space, you can't guarantee that you can reassign everything exactly, especially if you're using segment with base and limit, right? So the next idea is, well, instead of doing all this variable length, everybody has a variable length. Let us now break the memory into pages. So when we say a page, we mean that the physical memory itself has been broken into pieces, has been broken into blocks. So if you ask, so that's why when there was a file, let me go here, right? If I have a file and I just put a little amount of information in there, it still says 1 kilobyte. Because what? As far as even the hard disk is concerned, he's doing the same thing. He's allocating in blocks and blocks, right? If you right click and you say you are formatting, I won't format my computer for real, just to show you as an example. Right click, properties, okay. Okay, this is dangerous, but okay. He's not even allowing me to see what the, hey, you better not, okay, cannot format, that's good. Usually he should give me a warning and then, okay, let me see if I can get, he's not telling me how he's breaking it down. Usually you only see it when you're trying to format. He may tell me you can't format this either. Okay, good. So if you say, don't go and say start. Let me, okay, move this away and tab away so that it's on cruise. Okay. So if you look at it, it says, oh, I have some memory. But he says there's an allocation unit size. That means that his idea is that even for the hard disk, he plans to what? Break it into chunks. Are people understanding that concept? To manage it, all he's going to do is what? Break it into chunks. The moment he breaks it into chunks, that means that now he can know that, oh, I am dealing with, and he has a fixed list that he's dealing with. That, okay, whatever the hard disk size is divided by how many chunks I've broken it. I have a fixed array telling me what I'm using. If I have a fixed array, I will also be able to easily manage which ones are in use and which ones are not in use. So you can think of land. If land were such that everywhere it is variable, someone has 1 meter, someone has 2 meters, someone has 5 meters, someone has 1 kilometer, it becomes a little bit difficult to manage, especially when people are coming, leaving, going, coming, right? But if you just make it into a grid, now when you are managing it, you just say, okay, grid, you just check off. If you are doing who is using it, it's easy to just mark it 01 to indicate someone is using it. If someone is, if you're trying to search, for example, you know that there's a fixed size for what you're going to search. So by breaking into blocks, you have all these nice advantages. If you break into blocks, you solve the external fragmentation issue. Remember the external fragmentation was, you have these little unused spaces that will be cropping up if you are using variable length. So imagine if, depending on the size of your body, whenever you come to class, Ashes will make for you a special chair. What if you leave? If you leave the campus, you're no more coming, you've graduated. What are we going to do with that? The next person comes and says, oh, well, I want a little bit bigger, so we're going to cut off a piece and make you a bigger chair. Someone says, I'm so nice and trim, I want a very skinny chair to match my physique. We're going to cut off a piece. So over time, there are going to be all these pieces lying around, right? But the idea is, okay, now everyone has a fixed size chair, I think. Everyone has a fixed size. So it's easier to manage in that way, right? So that means we solve the external fragmentation issue. External fragmentation means we have allocated the chairs. There will not be any little pieces externally. That's our hand. I mean, we can still allocate. But then the internal fragmentation becomes an issue. But right now, I think memory is so much that for internal fragmentation, we don't think so much about it. We think, oh, I know some people still worry about it, that they don't have enough space for their movies and so on, right? And that's why often when you check a hard disk, you can find out that the size of the file you are checking. So let me see if I can do this. Right-click, properties. Let's see what this would say. All right. So let me print what this says. They have done well, but there's still a little bit of a difference. Copy to clipboard. Where's MS Paint? So currently I have my D drive, and you can see that the size and size on this, there's a difference. I hope people realize that. There's a difference between the size and the size on this. And in particular, the size on this seems to be a little bit larger than the size. So it means that even though he's allocating blocks, there are still all these spaces that are being left over. So you can say, oh, I've used my hard disk. And you say, okay, yes, I don't, if you have used the hard disk 100%, you say, okay, I don't have any external fragmentation. That means I've allocated everything. But internally, there's some space. Someone has used one character, left one over. Just like the file I made. I just typed less than 100 characters, but he's saying he's using 1 kilobyte. Right? So this concept is, if I use blocks, if I break it into blocks, I can solve the external fragmentation issue when I've allocated everything. But now, the internal fragmentation comes up. Right? Now, to solve these, some people would suggest, and last time I said it, that when programs run for a while, what the OS can do is periodically, it can rearrange them to try and make them a little bit more compact. So you can say, okay, oh, you are using this piece. Let's say you are using 2 pages. You have used half here, you have used half here. Maybe I can put the half together and give you one. As opposed to saying, use half of one page. That means internal fragmentation of 50% on each page. I can combine you into one. Right? So programs, when they are running, or even your hard disk, you can think of it as, there can be internal fragmentation, but compaction can help, but it won't necessarily solve it. Because if you decide to have fixed space blocks, then people may not or will not be using everything. You can't guarantee that, oh, every program should use 1 kilobyte. It won't happen. Or every program should use 4 megabytes. It won't happen. Right? So that means that your address, your physical memory is broken into blocks. And then if you hear this phrase, the process's address space, every process, as far as he's concerned, he sees that, oh, I'm using 0 to 1000. He has an idea that this is my address space. But remember that the address space itself may not be continuous. Let me just, there was one we just, right. So this, for example, he has an idea that, oh, my address space, I'm going from maybe 0 to 5000. He has an idea of where his address space is. But it will not necessarily match what it will be physically in memory. I hope you understand. The OS is the one who will do the mapping. If it's a segment, you map the segment, figure out where exactly it's going. So processes will have an address space. You'd say, I have a range that belongs to me. But that address space will or may vary from what it is physically. Right? So for the page one,
let's say that the processes range most likely larger than the physical range.
The processes range could be much larger or could be smaller. Right? So remember that as far as physical memory is concerned, by playing this trick with you, so I could tell you that, okay, I have, in this class currently there are, someone said 79 chairs. I could start a business and you could tell me, oh, okay, I want to have a conference for 100 people. I'll say, oh yes, great, I can handle 100 people. And I'll tell, okay, tell me when they are meeting. And you give me the different teams that are meeting. And so long as your teams don't exceed the limit, I will satisfy you. Because I'll just make sure that when a team is meeting, I say, oh, a team of 50, come along. Oh, we have a lot of space, come along. They'll meet, and then it looks great. The next 50 will come, they'll meet. So that means even though I don't have everything, by managing it, by moving the numbers up and down, that means that one day when people come, someone will be on seat number 1. Next day, I'll reassign him, depending on the space I have. So your space will be 100 people. That is for you a process, 100. But my memory, the number of chairs I have here is 79. And I'll manage it because I know that for a process, you can't possibly be using all your memory at once. I hope people understand that point. Process, you can't, I mean, even if you are doing calculation, you have to move one variable at a time. Like one or even a block. You can say a block. But so long as you can't use all at once, or the OS can play this game with the processes. You can say, oh, I'm a process. I want to use 16 gigabytes. The program will say, okay, my memory is only 2 gig. But it would still what? Be moving things in and out. In and out. I hope people understand that concept. You can't possibly use everything. So what? It's just like maybe take our canteen. Our canteen, we can't all fit there. But the idea is that hopefully we won't all want to eat at the same time. Maybe while some are on break, some are eating. I mean, people have their own means and ways. So the concept is you can have a fixed physical memory, number of blocks in there. And the processes can have a large process space. But then, since they cannot use all the process space at once, I was wondering why people are smiling. Okay. Or maybe people are planning for Valentine's next year. Don't worry. You are advised to start early. You shouldn't wait. But it's true. If you wait by January, it's gone. Okay. So you can use this algorithm for your Valentine planning. This allocation issue. You allocate the blocks, you go there and you reassign. Okay. So you realize that there is the physical address space, which is the space that the process thinks he's using. Right. But then the physical one will be broken into pieces, meaning that over time, as people go in and out, the OS will be what? Moving people, so it will tell you, oh, for your address space, go and use this space, this physical space for now. After you finish using it, you are kicked out, then someone else can come and use it. So you have a large address space, but physically, we may not have that much. Right. Now, there is a small example here, so it's a very small example, but it's to say that let us use 4-bit address. Right. The numbers here go from 0 to 15. I can just use Excel just to, where's my Excel? Excel, okay, that's my Excel. Hey, my Excel vanished. Okay, there's my Excel. Right. So address. So I'm told that my address will be 4 bits. You can do this for any number of bits, but I just use 4. Oh, this is so small. Right, 4 bits. So 4 bits is something like 1111. Right. So we are going to do a paging example. I'm going to say an address. And remember, the segment, when we're doing the segmentation one, it was an idea of use part of it to do the segment number and part of it for what? The offset. The page is a similar idea. So it's to say that your address space, if I say that, oh, the address in a program is 4 bits. So if you hear that currently we have 32-bit machines, if an address is 32 bits, it means that the largest address can be what? The largest space will be 2 to the 32 because you say 0, 1, 2, 3. So if I say 4 bits, that means that for a process, he can use from 0, 1, 0001, 00010. So all the addresses, that means there's a page number and a page offset. Same idea. The segmentation one, the only difference was that the pages were not fixed size. So I could just say, oh, here's a base, here's a limit. You give me your segment number, add your offset to it, I'll determine where to go. Right. So that means starting from 0, 1, what's the binary for this? If I do dect bin 1, okay, so 2 would be 10. I will also do, okay, how do I even do this? It will be, I wanted to make this appear as 4 digits. Come on, I know I can do this. repeat 0 for length of 4 minus this one is, and concatenate. Okay, so I did it. There we go. All right, so let's go. Going to go up to 16. Right. So you can see that for each one, I have 2 bits that I'm going to use. And say height. 2 bits that I'm going to use for the page, and 2 bits that I'll use for what? The offset. So that means that my address space, this is not adding, it's not going up. It's equal to this plus 1. Okay, now I have it going. So I can go 0, 1, 2, 3, 4, 5, 6. In the book, they are using the decimals, but I think when you look at it this way, you can see easier what it means. That means 2 bits for what? The page number, and 2 bits for the offset. Right. Now, if you look at this, that means that if I have a program like Notepad, as far as Notepad is concerned, he can think that, my addresses are going from 000 to what? 1111. Word 2 can be told, okay, I have addresses going from 000 to 1111. And then let's say Excel. Excel 2 can come in and think, I'm going from 0000 to 1111. Right. And then, because I've broken my memory into pages, I can trick all of them, not trick, but I can manage them, right? So if my physical, so let's say, now remember that these days when you're buying computers, sometimes they'll ask you, are you using a 32-bit machine? If you're using a 32-bit machine, what did they tell you about your memory? What's the max amount of memory you can use? Is it 6 gigabytes? Okay, let's do this. Let me see if I can. I think I have to watch what I type now, because there are other calculators. Okay. So 4 gig would be, okay, so this is a kilobyte times another 1024. That would be a meg times another 1024. That's a gig times 4. So this is 4 gigabytes in all its glory. Right. So one of the reasons why they will tell you that if you have a computer, depending on your address space, you also have a certain amount of memory. So if I have a 32-bit machine, that means that there will be 32-bit addresses, and the access is they call it like what's the word? An address that you have will also map to a 32-bit location. I hope you understand. So that means that if I say, address number 0, when I get there, I can have 32 bits that are there. Address number 1, 32 bits that are there. Address number 2, you can go on, keep going. Okay, so there has to be support. If you have a 32-bit machine, the machine itself, physically, the hardware, must be prepared to work with 32 bits at a time. Right? That means if I'm adding, and I say my OS is 32 bits, that means that the hardware itself, because what the OS will be doing is, he knows his 32-bit machine. That means that he's going to be moving instructions, everything as 32. And that means that when I say, hardware, add 2 numbers for me, I'm expecting that you can add 2 32-bit numbers. So the hardware is also part of it. I don't know if you remember the days of so people probably didn't remember 8-bit. It was 8 bits. It was like a Nintendo. They had this I think called. Okay, me, I was a Sega person, so I remember Sega Master System, 8 bits, Mega Drive, 16 bits, Sega 32, and so the Nintendo people had their own thing going. There was SNES, Super Nintendo, was 8 bits. Wait, Nintendo was 8 bits, Super Nintendo was 16, and then what next? Nintendo 64 went to 64 bits. So in the past, it was a matter of pride for someone to say my computer can do. So you add it there as part of the marketing, 64 bits. So when they were advertising the gaming machines, they used to do that, right? But now I think everyone has got it to 64 bits. So you don't see it so much that people say, oh, PlayStation 4, 64-bit. It's like, it's taking that. PlayStation 1, 2, 3, 4. One, I'm not sure if it's 32 or 64. I have to check. But 64, I mean, for someone to say 64, he meant to say, oh, 64-bit machine. That means that my calculations can be done with 64-bit numbers. And you realize that the colors, so going from the older computers to the newer ones, the more bits they have, the more colors what they can display. Because if they pick one pixel, they can say one pixel is maybe one address location. They can have more colors for it. You can try and simulate. So a 64-bit machine can easily simulate a 32-bit. Than it will be for a 32-bit machine to simulate a 64-bit. Right. For a 64-bit machine, pretending to be 32, all that you do is, worst case, you just say ignore half of the thing. Do the addition with just half of the number. And if there's any overflow, you just ignore it. I hope you understand the concept. But if you are going to be a 32-bit trying to run a 64-bit, so that's what you are seeing with your virtual machines. Those who don't have a 64-bit OS, trying to run a virtual machine which is having a 64-bit, the 32-bit has no idea. I mean, how do you deal with an address? Are you going to say, keep half here, keep another half somewhere? It's not going to be easy to even track the numbers. Because if you pick a number in 64-bit, how do you track all the pieces that are floating around? But for a 64-bit, you can easily run a 32-bit program or host a 32-bit OS. 64-bit OS. That means that the hardware is also 64-bit.
But then you make that calculation of 32-bit OS on it. Meanwhile, the system is 64.
Okay, so what will happen is this: if you have hardware, for example, if you have 8 gig of RAM, right, and you install a 32-bit OS, he will not be able to use all of your memory. So someone say, oh, go and buy more memory. There's a limit to how much he can take. Because the OS itself, as far as the addresses he's dealing with, there's a limit. So that means that even when he's trying to do, so you realize that right here, I was playing this game, over here, I was playing this game of, oh, there are all these segment numbers and there are all these addresses. Even if I'm mapping the addresses, because I'm using an address that has a fixed length, that means that there's an upper limit to how many addresses I can have if I say 32 bits. So you 2 to the 32. Let me see if that one will. Okay. Sorry. Let's see. 2. Where is power? I don't like. I need to move to scientific perhaps. Okay. Okay, this is 2 to the 32. Oh, I didn't do it right. 2 power 32. There's a limit. That means that the RAM itself, if you are saying you are 32-bit, there's a limit. If you're saying you are 64-bit, let's go see how. I think it should be to the 63 because 0 is not okay. But even so, you can see that. I mean, you have to probably you can keep expanding on and on and on and on until your heart. I don't know how much you can do if you told this is your RAM. I mean, I'll be in heaven. I'll be running everything, right? So just by saying that the OS has a certain address that is using for a certain number of bits for its address, it means that there will also be a limit on how much useful space one process can use, right? Now the hardware can play some tricks. So the hardware. So I was doing an example. Sorry, let's go to this. I have just 5 minutes. All things are possible. Hello. Say it again. Okay, so let me stop so that people can. But there's no class after my class today, right? There is. I thought Wednesdays there was a happy time. Like. Some of you are going to go to Bank of America. People are leaving. Okay, and also the ambassador thing. Okay, so today, Monday, Tuesday, I solved all my registry issues. So today I'll be fully available. I'm not going anywhere. Today, here, office straight. I'm not going to the registry. I'm not going to IT. I've solved my issues. Right. So If you have questions, please come by. Today, no more like I was here, I was there. Right. So just to wrap up, all I'm saying is for a process will think that what he has only 0, 0, 0 to 1, 1, 1. The physical space itself. So physically, I could just be dealing with 0, 0, 0 to 0, 1, 1, 1 as my space. But then, if you come to me and there are many processes running, what I'll do is I'll be remapping your pages. I'll be remapping. Anytime you come to me, I'll say, okay, for this address, go here. But the other thing I can do is, so right now you realize that I have, I've written 3 processes. That means that in total, this one is doing 15 addresses, this one is doing 15, this one is doing 15. The total right now, right, is 45. So in reality, the hardware will not have all 45 in memory. What you do is you play a game. If you ask me for a page and I can find it, so that means it's in memory. That's great. I'll give it to you. If you ask for more than I have in memory, that means that I'll take some pages that are here, send them to the hard disk, and then indicate that for this process, I've put your memory for that block in a hard disk. So for every block, if I say that I'm using 2 bits for the page and 2 bits for the offset, it means that every block, so if it says that 2 bits for the offset, how many things can I have in a block? I can have 0, I can have 1, I can have 1, 0, and what's the last one? 1, 1. That means that I have 4 addresses in a block. I hope people understand. Because of the offset, you can use the offset to decide the size. I hope you understand. The maximum offset. The offset goes from what? 0, I can do 0, 1, I can do 1, 0 to 1, 1. That means that within a block, I have what? 4 addresses. This is important. I hope people understand the concept. Okay, if I said that my page was 1, 1, 1 and my offset was 1, 1, 1, 1, what would be the size of a block? So my page is the first part. This is the page number. And this is the offset, the max offset number. So the block would be however many numbers I can have. What's the range? So that means the block will go from 0 to what? 1, 1, 1. So if it's binary, then that means that my block will be 2 to the, how many bits are here? 2 to the 4 minus 1. I hope people understand. So this is, I don't know, is it binary or COA come back to bite you? So you must get comfortable with what binary numbers. In that whenever you are given an address, so if it's a 32-bit address, some part of it will be for the offset. Some part of it will be for the page. But based on how many bits I'm using for the offset, you should be able to tell. Because if I say offset is, so this class, they are 79. If I say, oh, the maximum number for offset is 79, then you know that there are 79 chairs in a classroom. But if I say, okay, the maximum number of bits, so if I say, okay, I'm going to have all these rooms, and the maximum number of bits on a chair is 4. That means that how many chairs can I have in a room? It's the same question I'm asking. If I'm putting bits to number my chairs, and I say that, oh, every chair can have maximum 4 bits, then how many chairs can I have in a room? Isn't it simply 2 to the power, it's 16. I actually had it right here. This one, everyone has to, or people are still not getting it. You know binary numbers, right? Everyone knows binary numbers. 0, 1, 2, the second part. So I started with 2, 2, where we have an address that's 4 bits. 2 bits are for the page, 2 bits are for the offset. Right? And what I'm saying is, the first point is, the offset, the maximum number for the offset should hint to you the maximum size of the space. Right? If I say, for example, Ashesi rooms, I tell you, okay, I'm going to number the beds. The beds are going to be numbered from 1 to 10. And I tell you, okay, there are rooms, and all the beds, I always number from 1 to 10. You know that the maximum number of beds I can have in a room will be 10. Because that is my maximum. So the offset here, that's how you should treat it. As it's going to give you the idea of how large your block is going to be. So if I give you a block size, then the address in the block, you should be able to work back and figure out how many bits I'm using for offset. So if I said, okay, I'm going to use, instead of 2, I'm going to use, in this case, 4 bits for my offset. That means that my block can have a total of 16 addresses from 0, 0, 1, 0. So 4 bits, if you count in binary, there are 16 addresses. If I said I was going to use, let's say there's a 32-bit address, and my offsets will have, let's say, 20 bits. So what would be the address size for the block? How large would the block be? It would be 2 to the 20 minus 1. Because if my offset is 20, that means that anybody will be saying, okay, I can count up to 20 within a block. It's like buses. Maybe buses will work better. If I tell you that, okay, every bus can hold certain numbers, and I can number you from 0, 0, 0, 0, 0 to 1, 1, 1, 1, 1, 20 ones. How large is 20 ones? For those who are, so if you are, not scientific, I have to stop very soon because the people who are doing this are going to leave. In Windows, there's a programmer version of the calculator. For those who want to get comfortable, when you enter a number, let's pick decimal. When you enter a number, it shows you the decimal, the hex, and so on. So you can enter a decimal number, and as you are doing so, it shows you what's a bin number, and as you are entering, it can show you what the decimal will be. Right. So it means that for any number of bits, I have an idea of how many spaces I'm using. So I'm just multiplying 2 to the power something minus 1. But I'm just saying that anytime you're given an offset, so if someone says that the number of things in the room is this, or the maximum number is 20, you know that it's 20 per room. So that's what the offset is. Right. But that means there's a page number that's representing the room number. And then the offset. So all the OS has to do is keep track of everybody. When you say page number 1 for her, which page does it correspond to in the physical? Which page does it correspond to on disk? So he has to just play a game of moving around the different pages. But now everybody has a page, not a range. The segmentation was using range. I give you a base and a limit. But now it's saying, here's a page for you, here's a page for you, here's a page for you. But then even though you ask for a page, within the page, you have An offset. So every address has a page part and an offset part. Okay, so he's come for his people. Or for me. Okay, so there's a talk by the Italian ambassador. So that means I won't take any questions. Please make sure you attend this talk, right? Yeah. So please make sure you attend this talk. I have class from 11:50, but at 1:30 I'm free. So all afternoon, come by the office with your questions. So please, guys, we are really trying to encourage some of you come and sit on that session. And so I'm going class to class to make sure people are aware. Because I know I said I didn't see the email. So can we go there now? I haven't planned yet for Friday. The quiz is now much more likely be online than